Okay, section 5.5 is sort of a special way that we use probability to find what's called the expected value or the expected winnings when we play a game. So the expected value of a game is the measure of the average amount you would expect to either win if it comes out a positive number or lose if it comes out a negative number. When you play what's called in the long run. In the long run means if you played this game many, many, many times, or if a lot of people played this game, this is what we would expect the average to be. It doesn't mean that's what the average is going to be. It's just what we would expect it to be. All right, so to give you sort of a simple example of what we mean by in the long run and the expected value. So suppose you flip a coin 10 times. Again, based on probability, half of the time should come out heads, half of the time should come out tails. All right, so because we have a 50% chance of getting heads on each flip. Does that mean if you actually flip the coin 10 times, you're going to get 5 heads and 5 tails? No, probably not, actually. What it is again what the expected value is if you do this a bunch of times. So if you flip your coin 10 times a bunch of times. So you flip it 10 times, you get maybe two heads once. Flip it again 10 times, you get 10 heads. I mean, that can happen. Flip it again, you get 4 heads, 6 heads, 10, 5, whatever, all the numbers in between. If we did it a whole bunch of times, we would expect the average, if we take the average of all of the coin flips, it should average out to 5 out of 10 times. The more you do, the closer to that average you get. So the bigger the grouping, the bigger or the more number, again, in the long run, the more times you do it, the closer you get to the actual number. All right, so again, it predicts what an expected population mean would be based on probability and law of large numbers. Again, you're going to do the experiment a large number of times, or many, many. Suppose you have 1,000 people flip the coin 10 times. Some of them will get 5 heads, some of them will get less than 5, some of them will get more than 5. If we averaged out all of the coin flips, it should be pretty close to 50% heads. All right, that's what this means. So again, that's what this expected value means. If you repeat the experiment many, many times, that's what the long run means. Or if many, many people do it, we would expect that experiment to come out to what we would predict the population average to be. In this case, the population average would be in 10 flips, half of the time it should come out heads. 5 out of 10 flips should come out heads in the long run. All right, so that's what we're basing this expected value for a game winning and losing. That's what it's based on. So calculating the expected value for a game. So this is the expected winnings when you play a game of chance. That's what this is. If you're going and you're going to play a game of chance and you're expected to win this amount or lose this amount based on the probabilities. All right, so the expected value, which again is based on the probabilities and the long run, meaning if this is done a lot by either a lot of times by the same person or a bunch of different people. The expected value is the probability that you win the game times the profit. The profit is the amount of money that you win, right, if you play the game, minus the probability that you lose times the amount of money that you lose. And the loss can sometimes mean what you pay to play the game, right? That's the loss, right? I pay X amount of dollars to play. I have a chance of winning Y amount of dollars, all right? Then there's a chance to win and there's a chance to lose. The probability of winning and losing is that simple number of favorable outcomes to win divided by the total number of possible outcomes. The probability that the basic probability that we looked at early in this section. The probability of losing is the complement to that, which means if I have a 5% chance of winning out of 100%, that means I have a 95% chance of losing, right? Or a probability of 0.05 chance of winning, that means I have a probability of 0.95 of losing. Again, it should always add up to 100%, right? Those are your two outcomes. You either win or you lose. There's the chance of winning and the chance of losing. And then again, the profit in this formula means the amount of money you could win, and the loss is the amount of money you would lose. And again, losing could also mean the amount in your payout when you pay to play. All right, so let's do a couple examples. A fair dice is rolled. All right, if the number 5 or 6... If you roll and the number 5 or 6 pops up, then you win $10. Otherwise, you lose 6. Calculate your expected winnings. All right, so remember, the probability or the expected winnings would be the probability you win times the profit which is the amount you could win, minus probability of a loss times the loss, the amount you'll lose. Alright, so probability that you win, well, you win if you roll a 5 or a 6. Remember, rolling a fair dice, there are 6 numbers. Rolling a fair dice, you can roll 1, 2, 3, 4, 5, 6. 5 or 6 are the chance you win, which means these is the chance you lose. So the probability you win, well, you have 2 chances out of 6, right? There are 6 things that you can roll. 2 of them will give you a win. There's always a good idea to reduce it. That reduces to 1/3. Then if you do win, your profit's $10. You'll win $10. Probability you'll lose, well, that would be 1 minus the probability that you win, which should be 2/3. You could also figure out losing without doing the 1 minus, right? You have 4 chances out of 6 to lose, right? If you roll a 1, a 2, a 3, or 4, you lose. That does simplify to 2/3. When you lose $6, right? You have to pay them $6. All right, so those are the numbers that go into the formula. All right, so the expected value when we win, the probability of winning is 1/3 times the amount we win, which is $10, minus the probability of losing, which is 2/3, times the amount we're going to lose, right? So this is what we could win. This is what we could win based on probability. This is what we would lose based on probability. Those are based on, again, the chances. And so it comes out to 0.6. So I'm just going to round to the penny since we're talking dollar amounts. All right. So again, this is if we play this game in the long run. If I play this game many times, or if we have a bunch of people playing this game, they'll win some, they'll lose some. So they'll win $10, they'll lose $6. We would expect the average to be, well, it does actually come out to a positive dollar. So it comes out to be a positive 6.7. So the average would be that amount in winnings. Again, we win some and we lose, and we don't win 67 cents. We're going to win $10. We're going to lose $6. When we average out all of our $10 wins and all of our $6 losses, based on probability, we would expect that average, if I played this game a bunch of times, to be about 67 cents ahead. Alright, let's look at the next example and then we'll stop there. Alright, so we have a pair of dice that's rolled. The sum of the dice is a 2 or 12. The player will win $25. If the sum is 7, the player will win $7. Otherwise, the player will lose. So this one actually has 2 winnings. There are 2 things they could win. Alright, so we have 2 ways to win. And two different amounts that we could win. So when we find this expected value, the expected winnings, it's the probability of the first win times that profits of the first, plus the probability that you could win the second winning type times that profits, profit 2, minus the probability that you lose times the loss. Alright, so there again, like I said, there are 2 ways to win this. Alright, you can win if you roll a sum of 2 or 12. And so remember, you can look at the sums, that's the dice here, right? Our dice example. So a sum of a 2 or a sum of a 12, right? When the dots add up to 2 and the dots add up to 12. So there are 2 ways. Remember, this is a total of 36 total. So there are 2 out of 36 ways to roll a 2 or a 12. Alright, so probability of the first win would be a 2 out of 36. The winnings, the profit in that case, is $25. Alright, so that goes in the first piece. Probability of the second way to win. And the winnings in that case, I'm going to write that out. 7. Alright, so the sum is a 7. So again, remember, the sum of a 7 is when these add up to 7. That's this set here. Right? A 6 and a 1, a 5 and a 2, a 4, and so on. So there's 1, 2, 3, 4, 5, 6 ways to roll a 7. Alright, so the probability of winning the $15, or sorry, the $7, not the 15, is 6 out of 36. Alright, then the probability that you lose is anything else. So again, you can add those two up and subtract them from 1. You would have to add those two up and subtract them from 1. So 1 minus the chance of winning. So 2 out of 36, 6. So 8 out of 36 chance of winning, which means when we subtract that from 1, there's a 28 out of 36 chance that they're not going to win. Right? And then the loss is $15. Right? Or you could count it up all the other ways you can win too. It should be 28 out of 36. Again, that should total 1. When I add my 2, my 6, my 28, that should add up to 36 out of 36, which is 1. Alright, then you plug, so there's the numbers that you're going to plug into the formula. And so the probability, I'm just going to leave them exact. So 2 out of 36, you win 25, plus the second way to win, which is 6 out of 36 times 7, and make sure that looks like a 25. So I type it in correctly, minus the chance that you're going to lose, which would, there's 28 chances out of 36, times the $15 if you lose. Now again, based on this, it looks like you should win, because there's 2 shots to winning, but the probability of losing is actually fairly high. So again, this is going to come out to be, if you type it all out, so you get your, make sure you're careful with your fractions. I would put parentheses around mine just to be on the safe side. And so we get, it is going to come out, on average, you're actually going to lose about $9. Alright, so those would be the average losses. Again, sometimes you'll win 25, but the probability of winning 25 is fairly low. Sometimes you'll win 7. The probability of winning 7 is a little higher than winning 25, but again, that number is fairly small. Again, it's based on your average. So you win 25, you win 7, but most of the time, right, because that's a bigger probability, you're going to lose 15. So when you take your gains and your losses and you play this game a bunch of times, you actually come out to, on average, losing about $9. So in the long run, which again means after playing this game a bunch of times, or a bunch of people play this game, the average expected winnings, in this case is a loss, is a loss of about $9. Alright, we'll stop there. We'll pick up more examples in the next video.